Hey everybody, welcome to Inverse Functions with me. Today we're going to talk about undoing a function's actions properly. Technically what we've learned in pre-calculus, square root is the inverse of x squared. It's not technically correct, or it's correct, but we weren't precise about it in the way that we should be. Let me explain. So an inverse function is defined by saying we can take the composition of f and g on both sides and get back the identity function. And the g function that would do this is going to be called the inverse of f, and we denote it with this little -1 exponent. The problem. So notice this guy and this guy match up. If we were to talk about the function from r to r, where f of x is equal to x squared, which is usually what we think about, but then if we do the function for square root, if we do it from r to r, we can't plug negative numbers into the square root, which means this isn't even technically a function. We have to restrict this, which means that f also has to be restricted. And just there are even more restrictions. So we were not very precise back in pre-calculus, but now is the time to be precise. Using this definition, we can prove whether or not things are going to be inverses of each other, and it's going to look very familiar. Let's take it for a run. Let's say that we have f, and it is going from the positives including 0 to the positives including 0. So does g, and we have f of x is the x squared and g of x is the square root of x, and we want to prove that these guys are going to be inverses of each other now that we have the correct domains and ranges for everybody. All we have to do is do the composition, which I always find it easier to turn around and immediately write it like this. And then we have g of x squared, which is going to be x squared square rooted. And then we don't have anything to worry about because x squared is positive, right? Squares are always positive. But this is the positive square root that we're talking about. And so we should get a positive number out, which we will, since x would have come from the land of positive numbers. Okay, so that is how you safely take a square root. Now, let's try again. Do composition the other way. So g is inside of f. G was the square root. And then this one is less scary to do. That falls out just fine. Okay, there we go. We indeed get out the identity function when we do composition both ways. They are inverses, or g is f's inverse. Let's take a look at another function. Let's do f going from r to r, g goes from r to r, and we have f of x is 3x plus 2, and g of x is x plus 2 over 3. Are these inverses? Let's start with g composed with f. So then f is going to go inside g. So g is going to be, what is it? G of 3x plus 2, which means all of that gets inserted into that little x right there. So 3x plus 2 plus 2 over 3, which is 3x plus 4, and that's just not x. So you can stop here. You do not need to do the f composed with g case because it has to fulfill both of them, and one of them didn't work. So g is not f inverse. Okay, so in my opinion, that begs the question, just okay, so I can now check if something's an inverse, but how do you find an inverse? I'm pretty sure that this process is also going to look familiar to you. Here are the steps. What we want is we have a function, and we're going to set its output to be y, and we want to switch the x in the y role. Why? Because if we now solve for y while they've been switched, that means you have to undo everything that f does. So every step in solving for y undoes f, and that will leave us with f inverse. So let's try. Let's find the inverse of f of x where that was 3x plus 2, since the g that we had before was not f inverse. Let's see. So step 2 is switch, or did it, step 1? Goodness. We say that y is equal to f of x, where f of x is 3x plus 2. Step 2 is we switch them. Step 3, we want to solve for y. And now we conclude that y equals f inverse, aka f inverse is going to be equal to x minus 2 over 3. There we go. So even if that isn't a familiar process to you, hopefully it's not like too hard to pick up. First big theorem that we're going to talk about is the conditions for f to be an invertible function. F is invertible if and only if it is a bijective function. This is equivalent to 4.4.2 in your book. I just thought it was hideously terrible to read, but that's the spirit of 4.4.2. But I have relabeled it as Gracie 1 because this is a much easier thing to read. I hope you agree. Let's try and prove this though. Step 1, it's an if and only if. So we're going to have to go both directions. So that means the first thing that we're going to say is f is invertible is going to imply that f is a bijection. And then we get to start with 1-to-1 because f is a bijection means it is both 1-to-1 and onto. So we're going to say that f is some function going from a to b. We don't know what they are, and it does not matter. And then every good 1-to-1 proof starts with there exists two elements in A such that the outputs are equal. And what we're looking for is for x and y to be equal to each other. So since f is invertible, we know there exists an f inverse such that f inverse composed with f of x will just give us x back in general. Or I'm going to use a different letter since we are using x, such that a. There we go. For every single a in A. That goes for x and y. So then we just take the f inverse of both sides of this function, or this equation right here. There we go. We are left with x is equal to y. So therefore, f is 1-to-1. Okay. Let's do onto next. So remember, onto, we start with a random element in the range, or the codomain, I'm sorry. So random element is going to be in the codomain, and hopefully it's in the range. We will prove that it's in the range by finding an input that's mapping to B. So if B is in B, then since F is invertible, so since, we have F inverse is going to go from B to A, is a function that exists. So F inverse going from B to A exists. So then F inverse of B is going to be an element of A. So then we can just take F of F inverse. And we know that F undoes F inverse, right? Composition. That's just going to give us B. So then this guy right here is our candidate for A. So there exists an A, F inverse, B, such that F of A is equal to B. Therefore, we have that F is onto. So that's one direction. We have one-to-one, we have onto. Let's take a brief moment to conclude that F is a bijection. Therefore, F is bijective. Okay. It's one direction. Let's go the other direction now. So going backwards, we're proving that F from A to B is one-to-one and onto. So it is a bijection, implies that F is invertible. So let's start our proof. Suppose F going from A to B is one-to-one and onto. And that X is going to be an element of B. So then, since F is onto, we're like, big idea. We have to find the G that's going to work so that we can get this composition. So that's the big goal. We want to find the G so we can do G composed with F is the identity, F composed with G is the identity. Okay, so since there is an X in B, I know that there's an A, there exists A in A, or sorry, not X, P, such that F of A equals B. Why do we know that? Because F is a bijection, specifically F is onto. Okay. Then what's cool is that A is going to be unique. Why is it unique? Because F is also one-to-one. So we can't have more than one A mapping to this B, otherwise it breaks one-to-one. So then what I'm going to do is I'm going to use this information about A mapping to B to define my function G. So define G being a function going from A to B, or B to A, and it's going to be defined using G of B equals A. Same A and B that we've talked about over here. So now we can say that G is a function because there won't be more than one output for G of B. Why do we know that? Because that's why the one-to-one is so important. Otherwise, we don't get to define G as like an actual function, and we need our inverse to be a function. Okay, now that we have a definition for G, it's time to check, is this the inverse? Well, the only way to determine that is to start doing some compositions. So if we do G composed with F of A, we need to get A back out. So that's the same thing as G of F of A, which is going to be G of B, which is A. Perfect. Now we're going to do it the other direction. So then G of B is an A, which is B. So there we go. We have identity function. We have identity function. So then G is the inverse of F. Therefore, since we were able to find the inverse, we can say that F is invertible. There we go. All done. Okay. Now that we have this theorem, I want to go back and talk about the example that we had at the beginning about F going from R0 to R0 plus, where so F and G, we're both doing this. And then F was x squared. G was root x. So what wasn't going to work was just restricting the range for F. So give me a moment. I'm going to make a point. Okay. So originally what I had talked about was the obvious thing that we had to restrict the range. Otherwise, G was going to have like negatives plugged into the square root, and that's bogus. But then in the example, I took it another step. I restricted it to the positives in the domain as well. So why did I do that? Because F has to be a bijection. We just proved it. X has to be a bijunction. Why? Why would that break? Let's look. Let's say that we have left it like this. If you try and like just plug a general element in, the nuance gets lost. It is really hard to see. Let's try a specific element. Let's try x equals -4, right? We got rid of the negatives because the negatives are causing some sort of problem. What do they cause? So if we do G of F of -4, then that's going to be G of F of -4, which is G of, let's see, -4 squared, right? Yeah. Okay, so we're going to square that. That's going to be 16. So then square root of 16 is 4. So here you go. 4, -4. I've gotten something different back than what I started with. G is not the inverse. So that's why you have to restrict the domain for F as well. And now that we had bijection, I felt like that was kind of a more natural segue into this. But anyway, what you learned in pre-calculus, it's only like a little bit of a lie. They are inverses just as long as you define them correctly. All right, we have 2 more proofs, 2 more theorems. This first theorem really does kind of follow from the definition of inverses, but we're gonna prove it anyway because it's just a simple like element chasing set argument. We've got the domain of f is equal to the range of f inverse. We have the range of f is the domain of f inverse. I'm going to prove this first one, and I'll leave the other one for you guys to do. You're welcome. So proof, only doing that the domain of f is going to equal the range of f inverse. So subsets. First, this direction. So that means we say let A be an element of the domain of f. Then we can say that f of A is equal to B, which is an element of B. And then f inverse would then be this by definition of inverse, which means that B is input for f inverse. So then B would be an element of the range, or A would be an element of the range of f inverse because it is the output. Okay, so that's subset containment one way. I think I'm okay. So now we go the other direction. We say let A be an element of the range of f inverse, like that. Now we can conclude that since it's in the range, it has to have like an input that got mapped to it. So then there exists a B in B such that f inverse of A equals B. And then we can flip that around. I'm doing this right? No. I defined that backwards. A is in the range, which means it has to get mapped to. There we go. Now I feel better. So A is now an input of F, so A is in the domain. Okay. And then I'm kind of missing. Oh, I hate loose ends. There we go. So notice I didn't just flip the steps around for this one. Like the steps don't flip around that nicely because of when the existence quantifier gets used. You have to be careful about that, and so it's better to do it in two separate directions by themselves. Now we have box. There we go. And then next what we have is the inverse of F inverse is just F itself. So we know how to prove inverse things because that's just take a bunch of compositions and you'll eventually get there. Okay. We're going to say let F go from A to B. We're going to say and F inverse is going to go from B to A. What we can say is, see, we could start taking some compositions. We could, or we could start trying to be clever, and I vote for clever. So what I'm going to do is I'm going to say that this composition, right, F inverse composed with its inverse is going to be the identity. But you know what else is equal to the identity? F composed with F inverse. So now I'm going to start getting a little bit creative. So we have F inverse inverse composed with F inverse is now equal to F composed with F inverse. What we can't do is we can't just go, oh, they cancel. It's not allowed, guys. So how do we undo this? How do we get rid of him? Well, we know that if we compose it with F, we'll get the identity function. Like, I don't want to replace that with the identity function. We need to get rid of it on both sides. So we're going to add another F composition. See, like that? And then we'll do it to this side as well. And so then we have these groupings, and now we can put identities in for this guy. And so now we've isolated the F inverse inverse. Mwahaha. So then from here we have F inverse inverse composed with, that's going to be the identity function on A. F composed with A. There we go. And thus we are left with F inverse inverse is equal to F. Okay, there we go. And that is the last proof that I have for you guys today. Yeah, that's inverses, lots of compositions. I'll talk to you guys later. Bye.